All right, grade 10s. Last time I was with you, we were discussing understanding motion based on graphs, a position time graph or a velocity time graph. So before we leave this, I just wanted to take a look at these more complicated graphs and explain them a little bit. On your test, practically, you won't be seeing anything quite as difficult as these, but let's try and get a grasp of the motion anyways. So guys, what you're going to see on the left side, we're going to have our position time graphs, and on the right side we have our velocity time graph of the very same motion. On the slide you saw before this, what made it a little more confusing was that the velocity time graph was on the left and the position time graph was on the right. I think it's a little easier to understand if I split screen it and go with it that way, all right? So let's start with this object, which we may have looked at already, but let's quickly look at it again. So we have an object that's starting ahead of the starting line. Let's use sprinters. We have a sprinter starting ahead of the starting line, and they go backwards towards the starting line. They go behind the starting line at a constant velocity. We know it's constant because it's a straight line. Remember that velocity is the slope of the line. All right? Now, how does that translate as a velocity time graph? Well, they go backwards, right? So their velocity is negative. So they have constant negative velocity simply because they keep going backwards. And we know that it's constant. So there's no change in velocity. So it is a straight horizontal line. Now remember that the slope of the line on a velocity time graph is acceleration. So here we see no slope, so this object has no acceleration, which of course we expect looking at that right there. Now let's look at the next one, the middle one. Again, we have our sprinter starting ahead of the starting line, and just like before, he's heading back towards the starting line, but not at a constant speed because we have a curve. So a curve implies acceleration because we have a changing velocity, a changing slope. Now the slope starts steeply, so we are going backwards at a fairly quick rate, and then we pass the starting line, getting slower and slower and slower until here at 2 seconds or time of 2, there's a stop, and then we reverse and head back towards the starting line, getting faster and faster. Okay, so what does that translate like in a velocity time graph? So we start with our negative velocity, right? Because we're going backwards. But our velocity, which starts at a high negative number, is getting less and less and less. So we're getting slower, right? However, the confusing part of this is that is still positive acceleration. I know it's positive acceleration because I have a positive slope. A matter of fact, the acceleration is constant because when we're moving backwards, and we get slower, as if the acceleration is a force slowing our speed down, that means it's negative, it's still a positive acceleration. And then when we hit the starting line, right, we then go forward in getting faster and faster. And that's easy to see is positive acceleration, right? But it's also positive acceleration when you get slower going in a backwards reverse direction. That makes it quite complicated. Now, let's look at our last situation. Again, we have our runner starting ahead of the starting line. Again, moving backwards towards the starting line, but this time we start slowly and get faster and faster. So this portion of the movement is represented by this portion here on the velocity time graph, right? We start and we start like pretty much with a zero velocity because it's flat here, but then we get going faster and faster and faster. Now, ladies and gentlemen, this is an example of negative acceleration. The slope is negative, so going backwards, faster is considered to be negative acceleration. And then at the starting line, we're going to continue to go behind the starting line, but again, we've got a straight line there, so that is a constant velocity, right? So at exactly that same point when we hit the starting line, we now have a constant velocity, 0 acceleration. So I hope that makes a little more sense. However, again, you will not see anything quite this complicated when we get to test time. Now, folks, we need to cover a very quick lesson, really, on kinetic energy. It takes no time to tell you what kinetic energy really is a measure of and how to calculate it, and then we have 3 examples to look at. So, kinetic energy, as you probably are already aware of, is the energy of motion. Anything in motion has kinetic energy. Now, kinetic energy is based on really 2 properties or characteristics of matter. One is mass. So the more massive something is, the more kinetic energy it will have, and also its speed. All right, so its speed is also going to determine its kinetic energy. Faster objects will have more kinetic energy, which leads to the formula for calculating kinetic energy. So kinetic energy is equal to 1/2 times the mass times the velocity of the object squared. Okay, so by the way, units are very important. Units must be in kilograms for mass. Generally speaking, in physics, kilograms is our basic mass measurement. And whereas in chemistry, it's quite often the gram. Our velocity needs to be in meters per second, not kilometers per hour, to make the formula work and to give us our units of joules for energy. All right? Now, just before we start looking at examples, if I were to ask you guys the question, between mass and speed, are they equally significant to an object's kinetic energy, or does one carry more weight than the other one? Pardon the pun, we're talking about mass. Okay, well, guys, speed actually carries more weight, ironically, than mass does. And we know that from the formula. Notice that the speed value is always squared, right? Whereas the mass value is not. So if I said, oh, we have an object with a certain amount of kinetic energy, and I double its mass, if I compare that to the same object and I double its speed, the object that I double the speed of would have much more kinetic energy. Because if I just double the mass, I double the kinetic energy, right? It's a 1-to-1 relationship. But if I double the speed, speed value is squared. So that would be doubled squared, or 2 squared, which is 4 times the amount of kinetic energy. All right? That's why something small but moving incredibly fast can transfer a lot of energy, kinetic energy, to another object, right? That's why getting hit with a bullet traveling at hundreds of meters per second is much more significant than something heavier, like somebody throwing a mug at you, traveling, which is much heavier than a bullet, but it's traveling so much more slowly that it doesn't have the same kind of impact. All right, let's look at some problems. All right, so what is the kinetic energy of a 1 kilogram mass moving at 4 meters per second, right? So that's the scenario. We have some choice answers here. Well, remember our formula is 1/2 mv squared. So 1/2 times 1, the mass, times 4, but we square the 4. Guys, most common mistake with these problems is that you don't square. Now, I know that's really hard for you to see. Let's see if I can do something about that a little bit. Not too well. Let me soften the light a little. All right, still a little challenging, but trust me, you guys have these slides, so just have a look at them. So guys, 4 squared is 16, times 1 is 16, divided by 2 is 8. So we get 8 joules. So if you chose 8 joules, that would be the correct amount of energy. But what if this mass was traveling in the opposite direction? So that if it's traveling in the opposite direction, we would have to give it a -4 meters per second for its velocity. Of course, the mass is a scalar, so that direction doesn't matter. So if we plug these numbers into the formula, we get 1/2 times 1 times -4 squared. So the negative gets squared, which makes it a positive, so we get the very same answer. So guys, energy is a scalar term, and direction will not be important for these calculations. However, units will be important. Joules for energy or kilojoules, as the case may be. Okay, 3 other problems to very quickly look at. So this question says, we have a car with a mass of 1,500 kilograms, and it's moving at a speed of 14 meters per second, which is about 50 kilometers per hour. What is the kinetic energy of the car? So this is a straight up question, all right? Problem to solve, right? So we identify our mass, we identify our velocity. It's the meters per second we want, not the kilometers per hour. We have our formula of 1/2 mv squared, so we're just going to substitute and solve. So we're going to take our half, which we know is 0.5, the mass, the velocity, we're going to square it, right? Now, depending on your calculator, you can do this all in one step, or maybe if your calculator doesn't, you have to do it in smaller steps. Always remember, guys, that exponents come first. So 14 squared first on your calculator, then the multiplication order will not matter, okay? And then we would get an answer of 147,000 joules. Now again, because of digits, we actually don't want 6 digits in our answer. One way to shrink the number of digits, change your joules into kilojoules. So if you can see this here, remember that 1 kilojoule is 1,000 joules. So we would divide by 1,000 and we would get 147 kilojoules. Even better is if we change it into scientific notation, because we were given 2 digits in our question, so we might only want 2 digits in our answer, and we would have to take our 147 and we make it 2 digits, so we'd round the 4 to a 5, so it'd be 1.5 times 10 to the, and remember, if I'm going to keep it in joules, it would be to the 5th, since we had to take that decimal and move it to the left 5 places. 1, 2, 3, 4, 5. So that's where that 5 comes from. Okay, so that was a straight up question, but what if you are asked to solve for, say, the mass, and you're actually given the amount of energy? So bowling ball example is moving at a speed of 2.21 meters per second. If the kinetic energy of the bowling ball is 15.7 joules, what is its mass? So again, we identify what the question tells us. We have a velocity in meters per second. We have a kinetic energy. We are trying to solve for the mass. Now, ladies and gentlemen, what I've done is split the screen to solve it 2 different ways. One way is to rearrange the formula for mass. And if we did that, depending on how good you are at rearranging formulas, your formula would be the mass is equal to 2 times the kinetic energy divided by the velocity squared. Or if we leave the formula as we know it, and then we substitute, simplify, and solve. So over on this side, you can see I've simply taken the values and substituted them in, remembering the square of the velocity. And if you do this on your calculator, you should get 6.43 kilograms. If you like to substitute, simplify, and solve, we take our kinetic energy, put it there. There's our half. There's our m, which we're trying to solve for. There's our 2.21, which we are going to square. So if we simplify the right side, I take 1/2 times 2.21 squared, right? Square first, multiply by 1/2, leaves 2.442 m equals the 15.7 on the left. Now I need m by itself, so I divide both sides by 2.442, so I get the very same answer. So depending on what you are more comfortable with, there you go. Typically, a physics student is going to rearrange formulas using algebra, and you would most commonly see things solved this way. Depending in grade 10, since it's introductory, you may not be pursuing physics 20, physics 30. So if you like the substitute, simplify, and solve method, well, there you go. Now, the last question, guys, is to look at a hockey puck. A hockey puck, remember when we used to be able to go to hockey games and play hockey? You know, a hockey puck has a mass of 0.21 kilograms. If the puck has 73 joules of kinetic energy, what is its speed? So again, we identify that we're given a mass in kilograms. We have our kinetic energy in joules. We're trying to solve for V. Well, again, split screen. If you rearrange the formula to solve for V, notice, guys, that we have, when we're solving for V, which was squared, we actually have to square root both sides to solve for V. So that's why we have this square root of 2ek over m to rearrange the formula. And again, if we substitute what we need to and we solve, we're going to get 26.4 meters per second. Again, on this other side, just doing it into substitute, simplify, and solve, we have 73 kilograms. There's the half. There's the 0.21 times v squared. Let's multiply these two things together. That gives us 0.105 v squared. 73 is still on the left-hand side. We're going to get v squared by itself by dividing both sides by 0.105. So we get v squared is equal to 695.2, but we would have to square root both sides, which leaves us with v, and the square root of 695.2 is 26.4, which of course gives us the answer that we expected. So guys, that is the speed of the puck. Remember, if you want to translate that into kilometers per hour, you would multiply by 3.6, which means that this puck is cruising, right? So just, you know, for our own knowledge, 26.4 times 3.6, the puck is traveling at 95 kilometers per hour, like cars on the Deerfoot, going slowly on the Deerfoot. Anyway, so guys, I think, yeah, we're going to be tackling potential energy the next time we see each other, but you will have some problems to solve regarding kinetic energy to work on. Until next time, thank you.